So thank you for coming to this webinar that we are hosting together with LB-DED. My name is Jesus Rodriguez, and I am the manager of the support team in Meltio. And we also have with us Michael Mead, expert of Meltio in 3D Byte. Thank you for joining, Michael. So this presentation is going to cover our partner ecosystem. We are also going to talk about our LB-DED process that focus on wire deposition, and also about the dual wire capabilities that we are having in Meltio, as you can print with more than one material in the same layer. Also, as this webinar is focused for research in institutions and universities, we also want to tell you and show you how do we parameterize our materials for our LB-DED process. Lastly, we will be talking about our slicing software and also about some applications that can be done with Meltio.
Yes, guys. So my name is Mike Mead. I'm the Meltio technical lead in the UK. So I work across two companies, 3D Great Britain and Ireland, which is our industry side. And then today's focus, I work for Create Education as well, which are Meltio's education partner here in the UK. We work with all levels of education, from universities and research centres, tiering down through into sixth form and high schools. And the objective here is to further develop additive technologies within education and support the research from there. Okay, so why do Meltio manufacture LB-DED process? Our wired DED system is focused on production and also for research. We have a vision that is delighting our customers, partners, and also we want to have a really big ecosystem of universities and partners that help us just to develop the best process for the industry. We manufacture our metal DED systems in the most reliable way, just to focus on what we think that is the future, that is additive manufacturing with metal, to reduce cost and also to be able to focus on some markets that we have in scope. We have a big ecosystem of partners. We have already more than 300 systems in the market. We have a lot over here in Europe, also in the Americas and in Asia overall. We have more than 55 source partners and integration partners that are able to install and integrate our systems around the world. We have more than 13 software partners that have identified and that we identified with them that our system is capable of performing several geometries and several applications, and they have developed their software capabilities for being integrated with the Meltios. Also, we have more than 60 universities and technological centers that are already using Meltio technology around the world. Here, there are a few examples of partners in education that we are having. We have several of them, of course, also in the UK, but all around the globe, in the States, in Asia, in India, and of course, our main scope with them is just to help them, and also they help us pretty much on developing this new way of manufacturing. So as Jesus says, we've got multiple systems globally in lots of industries with a high prevalence in education. The aim of the Meltio technology is to provide a safe and reliable source for metal 3D printing. It's a perfect deployment in education because there's no need for protective equipment, ventilation, those kind of things, and big infrastructure changes. We've got safe, reliable, deployable systems that can produce metal parts quickly and unattended. The integration-ready systems mean that we can expand the boundaries of 3D printing by using integrations into CNC technologies or robot technologies. And our high spread across universities and technical centers gives a wide range of research. The fact that Meltio is a multi-metal 3D printing technology means that there are many fields of research that are open to us. The bonding between materials, the production of new parts using multi-materials, and the process
by which we get to that, and then the end applications for those parts. So the Meltio technology has a lot of scope for research and development and a change in the way that we manufacture products. So we'll have a little look at the video on the next slide, which will show us the process of the Meltio system. So what you can see as this is happening is we've got the wire contact coming down. That wire sits normal to the surface and is surrounded by 6 lasers. Those 6 lasers form a melt pool into which we feed the wire. This wire is held in place from the nozzle, which you can see at the top of the camera. And one of the things that you'll see here is that the wire never breaks contact with the part unless we want it to. So we've got a voltage system that runs a current through that wire. And what we're looking for is continuity between that wire and the part. So as soon as that electrical contact is broken, the system knows to feed more wire, which is one of the things that ensures us to get high density parts from our Meltio system. So we're getting densities in the 99th percentile for parts that are being produced. So if we go to the next slide, the thing to know about Meltio is that it is not trying to produce these niche fancy lattice parts that we see from powder bed fusion technologies. That is not the objective here. The objective for Meltio is to produce, a lot of people say near net shape parts. I say very near net shape parts, because the objective here is to produce parts that we can still finish through traditional methods, so CNC. We can use them as they are, but what we tend to do is we oversize the parts by about 1.5 millimeters, and then we can machine back to net surface, which saves us a lot of production time for other parts, but it also saves us in things like machining costs and makes the system greener and more eco-friendly as well. All of this is done producing wire, so there's no powder, no health and safety concerns from those areas. So we're not going down the niche, we're into the industrial applications. So let's take a little look at what wire laser metal 3D printing is and how it works. So I've touched on a little bit of this already, but Jesus, if you can give me the next slide, please.
Yes.
So we're looking at safe and reliable. These are 2 massive, massive key factors for all aspects of not only production, but education in particular. As we push the boundaries of something and we try and research, we have to ensure that the printing that we do is successful and safe and reliable. So with the print being done mainly around wire, then what we've got is safe, clean, and easy to work with feedstocks. There's no handling, no waste. What we've got is what we can use, clean, safe, easy to handle, no special training required. As I mentioned earlier about being integration ready, many universities have existing technologies that have been used for particular applications and maybe sat either idle or redundant. Meltio has the ability to be retrofitted into a lot of these technologies. So we'll see later some of the deployment, but we can actually retrofit into existing CNC machines, or we can fit onto existing robots and turn those into hybrid or machining centers for difficult geometries. Again, reducing the need to carry lots of metal billet and lots of feedstock, which reduces the need for holding all these things. We can just work with wire. The ability to print in multi-metals. So as I said earlier, again, we can look at the ability for hard facing or anti-corrosion applications. We can look at dual wire for creating alloys on the fly, or we can look at the ability to do support materials that are cheap and easy to remove for 3-axis systems. Lots and lots of applications for multi-material development. And it's accessible. So it's the only metal 3D printing system that's able to deliver fully dense and affordable metal parts within a few hours. There's no preheat times, no argon purging, none of that kind of processing. We put the model in, a simple software solution, load the model, and from pressing print to the first layer of material going down can be around 60 seconds. So as we look at the benefits of the parts themselves, we've got the process and that we've managed to manufacture these parts throughout. And as we've gone through with Meltio over the last sort of 4 or 5 years worth of production, the development of the process has allowed us to create parts with a better microstructure and a really dense material. So what we've got is the laser process, the Meltio process, uses a normal to the surface wire, which means our toolpath process is easy to generate. But also it creates a really low heat affected zone on the part. This means that we get a better microstructure in our parts. We've got less heating, less cooling. So the microstructure is tighter, and the overall density of the parts is better. As I mentioned earlier about the process control system, we have a really highly controlled welding process. So the normal to the surface wire and the constant contact with either the substrate or the part allows the current to flow, which we can then use to not only monitor the print, but with some of the upgrades as well to the system, we can put a hot wire through that wire, through that current. So we can heat the wire using resistance rather than just the lasers and speed up the production process even further. And my very near net shape parts, as it says there, you'll get these slides afterwards, but around 1.5 millimeters of oversizing gives us the parts that we need. And if any of you were present for Rocio's design guidelines webinar a couple of weeks ago, then you'll know that some of the design guidelines show us about minimal wall thickness and hole size. We've got an excellent part production with minimal design constraints. Okay, Jesus will move on and he'll tell you a little bit more about the print head and the actual structure of the printers.
So now I would like to talk, as Michael said, about our head technology. Overall, the lasers that we are using are direct energy position diodes. They are having a wavelength of 976 nanometers, and we are having a constant wave. It's not a pulse wave. We are using also a coaxial wire feeding that enable us just to feed the material completely coaxial in the head, while we are having the lasers being focused on several directions. We are having 6 beams coming from the diodes. So in total, we are having those 6 diodes that are collimated inside of the head. So the lasers are not inside of there. What we have inside of the head is the integrated wire feed system that is enabling the head to manage up to 2 materials at the same print and also in the same layer. In a print, you can just be using one wire while the other is completely folded inside of the head. And as soon as the process of depositing this wire, you can just retract it, and then you can just continue with the other wire that is being fed. Like this, you can achieve the dual wire material prints that also Michael was mentioning before. So layer by layer, you can have those 2 materials in several of the walls of the print, and then you can build the print up in the Z-axis direction, having those 2 materials in several points that you are wishing to. Also, this head is pretty much easy to service, as at the end, the feeding system is completely accessible. There are just a few screws away. You are just a few screws away from the actual drive wheels. And inside of the head, mainly you are having some cooling system, because the collimation of the laser needs some, let's say, some cooling, as there is a lot of heat in this part of the process in the transmission of the beam. While in the feeding system, the only thing that you need to take care is about the actual drive parts, that are the drive wheels, and of course the wire guides we are having. The head is completely hot wire compatible. Hot wire is a tool that also Michael commented before. We have the capability of having a continuity because we are always touching the wire and the substrate together. So the hot wire is just a feeding of a lot of current in DC by our deposition head, and then it has to go up to the substrate. We have a short, and the current just wants to flow through the head. Then we are having a 1 millimeter wire, 1.2 millimeter wire, and via there, a lot of current have to pass. So due to the Joule effect, we are preheating the wire, and all our systems are compatible with this option. That is also related, let's say, and also is completely compatible with the process control of the system. So we are having this current flowing in the head, and of course, we also have a control that is a pull-up that is coming also from the backside of the head that is measuring the voltage that you are having all the time in the melt pool. So as soon as you have any disconformity in the deposition, if there is any raise in the voltage of the melt pool, then you will have a correction directly done by the electronics that the Meltio have. And it's going to correct any kind of misprint that has happened due to any, let's say, deposition that was improper, setting in the slicer or whatever. The system is enabled just to perform this repair task in the same time that the system is printing. And just to continue with the understanding of the Meltio process, we are printing near net safe prints, as also Michael commented before. So we print the part, then we need to make a post-process that can be a 1 millimeter thickness wall that you need to remove just to have a completely flat surface. Sometimes, depending on the application, you don't need to, let's say, machine everywhere. You just need to machine where some screws are going to be, where a bearing is going to be also inserted, and in the areas that are really going to be used as a motion part. Or, for example, let's say that you have a piston. You will be in need, like in this example, of just performing this fine-tuning in the external walls and in the inner areas where you are going to have the attachment of the other part that is holding the assembly. Lastly, in case that you don't need to make any kind of treatment, you can just directly cut the part and use it directly after the printing process. So now I'm going to continue with printing wire and also with some of the portfolio of materials that we have already tested and fully developed as Meltio materials already. And as we also discussed it before, we have the capability of single wire. You can just make a long print, let's say, of 20 kilos with stainless steel. You can also make, let's say, combustion chamber that is having inconel in the inner area if it is going to have a big heat or any kind of chemical reaction. Also, you can have then stainless steel in the outer wall, because in this scenario, you don't need to have a material that is able to hold those high heats. But in contrast, you can have a cheaper material that have a cost in the market of around 20 euros, and you can have your cooling channels for the combustion chamber performed in this material. Also, something that we focus pretty much in Meltio is about the densification of the materials that we print. We have tested a lot of materials, and we have also focused our efforts on developing the most used materials in the industry. We have fully validated with completely 99.99 densification in terms of volume of stainless steel, inconels, titanium, and other materials that are pretty much used. We have our validation for all of them, and we will also discuss about it later on in the presentation. Also, about layer height, in our LB-DED deposition process, we are focusing on layer heights from 0.6 to 1.2 that we have found that are really stable layer heights that we are able to hold with our technology, and also with the wire range that we are using with the welding wire, I mean. So those are some of the samples that of materials that we have already developed. We have broadly printed several stainless steels overall. We have also focused on some carbon steel, like Milo steels, ER070. We have also printed several nickel alloys. Titanium alloys are fully compatible, hard-facing materials. We have already tested them with a really good printing process, also with copper alloys. And of course, this is not something that we just stop by there. We are keeping developing the technology. We have several new features that we are adding day by day to our technology. And also, in case that any customer wants to print a concrete material, in case that they are not completely validated Meltio materials, because completely validated Meltio materials mean we have the full densification process. We also make material testing, mechanical testing, like elongation and so on. For those materials, those are the ones that are Meltio materials, and the others we can also give parameters, and the customers can just focus on printing them or developing some other parameters. Overall, something that we focus pretty much is in those mechanical properties. To achieve them, what we do is to make several iterations with the materials we print. So first of all, what we need to do is we need to achieve the fully dense parameters. So we make some testing, we make some iterations until we get this consistent densification of 99.99. Then also, under some conditions, the roughness is important for our customers. So in case that they need to focus on a slow roughness because they don't want to machine, they don't need it for the process, they just go with a smaller layer heights and they are able to achieve some RA close to 12, 15, 18, depending on the material that is being printed. And also, of course, in case that is necessary any kind of post-process, then the customer can just like select between the processes that we recommend. We are having a material handbook where we are already giving several recommendations of how to perform all those processes just to make the life of the customer easier. And this is an example of the material properties we are able to get. As you can see, if you compare the Meltio as printed properties, then if you go with broth, casting, in the example of the stainless steel, we are getting better properties than with the regular processes that are followed in the industry. With titanium, you can also see what we are able to achieve in case that we are just like printing with our system and that we process the materials with the recommendations that we are giving in our materials handbook. Same for the Inconel. At the end, as our process is not having stresses and we are just generating a plasma between the substrate and the new wire that we are adding, we are able to get really good mechanical properties with high densifications, and the amount of residual stresses that are left in the part are pretty low.
I think it's worth saying to everybody that's on this call, I don't know if we said at the beginning that if you've got any questions, please add them to the Q&A, to the chat. We can answer them as we go along. And the other bit on materials is that the objective here is for education. So we want to further your research. Meltio does not lock you into a particular material. Both the Meltio Smart software on the machines and the software, the slicing software allows you to create your own material profiles. So if there's something outside of the Meltio family that you want to be researching and you want to look at development for, then that is up to you. You can try your own wire in the machines as long as the diameter is okay to fit through the feeders and the nozzle, then the opportunity is yours. Okay, so I'm going to talk to you a little bit about the dual wire side of things. So we'll start with the video. So what we've got here on the right, you can see both independent feeders. So there are two feeders in the machine, one sat in front of the other inside the head, and we feed both wires through the same nozzle. So the nozzle is set at the end of the print head, and 50 millimeters back from that, we have a sort of funnel, a buffer zone. Each wire can be independently tensioned so that we know for softer wires, things like that, that we can ensure the tension for the print. And a material change will take around 5 seconds. So this is live on the video. You can see how quickly that can be changed over. We'll get no cross-contamination from the two materials. And as long as the materials selected bond well together, you'll have no problems within your print. So if you can give us the next slide, please, Jesus. So as I said, it's a very easy process to adapt to. We don't need to go changing lots and lots of issues in the design. We would work as we would for any other dual material additive process. So I would design, if I was working in Fusion 360, for example, 2 bodies, 2 parts in SolidWorks. We export those and we add them to the software. We select which material we wish to print with, and we select print. There's nothing more complicated than that. The wire changing process will happen automatically. And as I said, it's a fast process, less than 5 seconds for a changeover. And because of the Meltio process, with no spatter from the part as you would get with a WAM process, 100% of the material is used within that part. So you're not getting contamination between your parts, but also 100% of your material is used within that part. Okay, next one. So here's a great example. Why are we looking at dual material? So this is a press brake tool. You can see the additive finish has been left mostly throughout the part with a machine surface on the pressing edge. But what we've done here is there is on the diagram in the middle what looks like a hollow section. That hollow section is the second material. So this part, for no other purpose than reducing the amount of cost to produce this part, has a center core of mild steel. So that center core has no other purpose than to carry the remainder of the model. So we print that, we maintain our product strength, we maintain the elements that we want from the tool steel, but we reduce the cost of the part significantly by being able to use a cheaper material throughout that core. That same technology, that same option can be applied for things like Inconel, where if we were looking at machining parts, we would just have an outer core as well, where we maintain that strength but reduce the cost and also the weight of the part as well. Okay, next. So this is a great example. So this is a mold for the bottom of a glass bottle. The original part was made in cast iron. I forget the details of the exact times, but the process for repair of this was to hand weld back on, taking several hours. With the Meltio system, what we can do now is we can fit this into a CNC. So we're talking hybrid applications here. The CNC process can machine down the worn elements of the mold, but we can't weld back on to, we can't weld the steel back onto the cast iron. So what we do is we create a layer in between, a sandwich layer or a butter layer, as you'll find it in welding terms. And we'll put that in with a nickel alloy. So this instance, we've got nickel, we've got Inconel 718. And then once we've got that interface layer of the 718, we can go back and create our molding structure using the stainless steel 316L and then machine that back to shape again. So we're being able to use the different material properties to allow us to access areas of manufacturing that we wouldn't be able to access before. Okay, next.
So now it's my turn, and as this webinar is pretty much focused on technical centers, universities, I would like to show you how do we parameterize our melting materials so you also have the ability of making the same process for your Meltio systems. So for us, it's important, first of all, to make the slicing easy as possible. So in the case of Meltio 450, we already developed last year our own slicing software that is focused in our technology. It's able just to manage perimeters, infill, hot wire, process control, everything independently and in different layers. Also, you are able to apply several modifiers that help pretty much for the parameterization of the materials and for achieving really good prints just in the first trial that you are performing. And then, of course, in the case of Meltio engine, we have a completely open software ecosystem. We have our solution for Meltio robot integration, that is Meltio Space, and we will talk about it later. But as you can see here, we have several partners that have already developed the software and their software solutions, integrating the Meltio configuration for being able to print with our system following high standards. Some important information. So first of all, in case that we are going to parameterize any material, we need to know the basic information of the wire. What is my diameter? What are the applications? What is the chemical composition, physical properties? So I know the base of what should I apply for. Let's say that I'm looking for an application that is using Inconel 718. I need to understand why, just for knowing exactly what mechanical properties I need to achieve for the material after the Meltio printing process. Also, as soon as we know the wire, we start our printing process. And first of all, we need to make some iterations with the material. So we are just selecting different velocities, different feed speeds, different laser powers, just to know what is the best configuration for my tomography test. In my tomography test, what I check is what we commented before. What energy density should I apply to my material to have fully dense parts? As soon as I have my parameters, I'm able to go with any kind of micrography or heat treatment recommendations, because I will have, let's say, an insights of the mechanical properties and the properties of the materials overall I will have after printed. What we do with the heat treatment is as follows. Let's say that, for example, we are printing a tool steel. A tool steel as printed can have like some internal stresses. So why not to make an annealing in this scenario? And this is something that we really recommend. So as soon as we just have our as printed material, we know exactly after some tomography, some micrography test, if we are having any kind of small crackings, any kind of residual stresses, after we also make some other checks. So with our material handbook, we just focus on the treatments that my customer will be in need of focusing. We give you also a close view of polished and etched surface for microstructure in those documents, so you exactly know for the melting materials that we already tested what you are able to achieve after printing them. And of course, for our slicers, we have the printing parameters that we have already tested. For several materials, I just said before the heat treatment example, but for several materials that you have seen before, a heat treatment is not needed. Of course, it always depends on the application. There are several applications that will never need a heat treatment, but there are applications that will do. And also for making it easier, with our build parameters that we give for Meltio Horizon, Meltio Space, and also for our software overall, you can just know exactly what to use in terms of using our materials. In case that you are developing your own ones, you can use them directly as a guide, and then you can just parameterize them following those basic recommendations. Always starting with a low speed, going with a high laser power, and have a good control of the position of the wire you are doing to achieve the best mechanical properties in the first trials of your material parameterization. So, important, this is the process that we have already proven that is the best for validating the materials with our process. First of all, we have a phase one. So we select a large range of parameters and we test them to define the process window. So let's say that we want to have a densification, depending on the application, of 90% to 99.998. So I can play with the actual variables as laser power, hot wire, position, speed, just to know what is my range of energy density for getting those properties. Then in the bulk density that we do, of course, we just check this density, and then of course the hardness. That is a test that is pretty easy to perform and is pretty quick. And it's something that all the institutions we work with have the capability of making them pretty easy. Then, of course, we just focus on the properties we are getting. So we make a selection of the results within the range of the test we did. And then we just make a build with sufficient samples. We just bring them to technological centers so they validate the process we follow it. And we test several attributes. We just make a second iteration of the density parameters, well, of the density of the parts we already printed. We make some hardness test together with the post-heat treatment capabilities in case that they were needed. And then we just make some basic mechanical testing like textile strength, and we check some metallography. And then we just go to the next and last step. That is the phase 3, where we check some more further attributes of the materials. That let's say that I have an application with a customer that needs to know what is the maximum fatigue that the material is going to be able to hold under certain circumstances. So together with them or with our technological centers, that I just want to mention that they really add a lot of value. All the universities and tech centers that we work with and that already have the Melt in their portfolio have helped pretty much during all the process. They make a lot of research, and I'm happy to work with some people that I can see inside of this webinar just following, and that have gave a lot of good results and a lot of good insights during those tests that we have performed. Metallography, impact, it really depends on the application that we are focusing. Those are some examples that I also want to show you. We have our process bands. Remember, depending on the application we have, maybe we are prototyping, maybe we want to have fully dense part for a concrete application, and we have our band. Those are the 3 bands that we tend to focus the most. So lack of fusion is a band where we are having, let's say, an amount of defects that is good for prototyping, but not for a part that will go in an aircraft. And then we also have in the middle some minor defects. For us, minor defects is something that goes from 98 to 99.9 density. We have really small defects. There are no porosity larger than 250 micrograms, and there are just defects that are appearing punctually in the printed part. And then, of course, we have the fully dense, let's say, parameters or fully dense band. That is where a lot of companies just work with for knowing that they are always going to achieve this 99.99 density. In here, you will not detect appreciable defects, and actually the density is evaluated through metallography, and those are the bands where we make the majority of our mechanical tests. Usually, we don't focus on the minor defects or lack of fusion. When we want to get the best mechanical properties, always we go with the fully dense parameters and we test what we achieve. We have also done with minor defects and so on for our utility profiles, for knowing exactly with big deposition rates what properties I'm able to get. And this is another example of the tomography. So in here, you can see the target that we are having, also the infill printed with insufficient energy density, and also in the left side, you can see the part that is having a fully dense. How can I correct the problem that I am having in the right side picture? So with medium to highest speed, I can have minor defects. Let's say that I want to have a deposition rate of, I don't know, a kilo for saying something. So depending on my energy density, I will have one result or another. I'm not going to be able to get, let's say, 0 porous if I don't control my energy density farther than the bands that we discussed it before. So depending on the actual diameter of my wire, hot wire I use, and also because the hot wire at the end adds energy to the equation, is an amount of wattage together with laser power. Let's say that I want to avoid completely the porosity in my part. I should always focus in the band that I mentioned before, the fully dense band, that in this case for the stainless steel starts at 122 joules per cubic millimeter. And of course, we have developed the technology for a while already. We have already seen what are the, let's say, variables that are affecting the process. We always focus with our toolpath strategies, with our software, with Horizon, with Space, on having those fully dense parameters, also in case that there is any other application for minor defects. And directly in our software, we have strategies for knowing exactly where can I have an overheat, so the part is going to just wait for a few seconds, not to overheat the area, what energy density I'm using, do I need to use a utility profile, do I need to use a fully dense profile, how long is going to last this print, how many gas I'm going to consume, material, what is going to be my cost, optimizing those toolpaths, optimizing the knowledge that we have inside of the software for every application and every print is going to lead to getting the proper mechanical property, the mechanical properties that you are in seek of. And those are the Meltio products we are having right now in our portfolio. We have the Meltio M450, that is a standalone system that is able to print in 3 axes and also make the near-net safe products that we commented before. We have the Meltio Engine CNC and the Meltio Engine robot configuration that are able to be integrated in several CNCs, in several robots, and you have the ability of printing with more than 3 axes. So you are not going to be in need of using supports. And then we also have a completely one-in-one solution that is our robotic cell, where we already integrate a robot together with the Meltio engine. And you have an area for the supplies, wiring, gas, and so on. So it can be easily moved around wherever is needed by the customer. Those are our software solutions that we also discussed before. I spoke a bit Meltio Horizon, that is our slicer for the 3-axis machine. And then we also have Meltio Space, that is our robot slicing solution that have several slicing strategies depending if we have a radial print, planar, and well, we have more than 12 strategies already. Depending on the part that you want to print, you can use different of them just to optimize the time for printing and also the way that the print is going to be performed in terms of optimizing. In case that I want to make cladding, usually I want to focus on a strategy that is going to lead me to starting a point and then to move a positioner, like in the example that we can see in the right side picture. In this case, it's not a cladding example, but we can just like start and make the rotation of the table while I am making the deposition. Meltio Space is optimized for several different ways of slicing.
So you're back with me. And as you've got two people who are very passionate about what they do and what they talk about, we've actually covered a lot of the information that's to follow. So I'm going to go quite quickly through these next couple of slides because I know we've got a few questions to answer as well at the end. So if you give me the next slide, please, Jesus. So when we talk about applications, we've already touched quite a lot on the dual wire capability of Meltio, the ability to do hard-facing, anti-corrosion parts, but also to be able to use the different magnetic properties of materials as well. We've got excellent mechanical properties from our parts and a really cost-effective method of producing them. So our Meltio process is a really high-efficient process for producing metal parts. And the very near net shape process means that we can reduce a lot of the processes, post-processes or roughing processes used in a CNC application, a traditional manufacturing application. So the drivers for adoption for this technology, particularly in education, it's the ability for access to a lot of materials without massive expense. So we're not having to buy different size billets and stock to machine from. We can produce our parts all from the same reels of material that are easy to store, no expiration date, and very readily available. We can get parts with a really complex geometry, extremely complex if we look at the turnkey robot cell or a 5-axis CNC deployment, and still highly complex with the 3-axis systems as well. Our typical part size, we work on mass, not geometry really. So somewhere between 1 and 50 kilos is the ideal. You can print smaller if required. So we tend to look at, if you look at smaller parts for a bounding box around 25 millimeters square, but nothing more than 2 meters really. Once you get up to those standards, it becomes more economical to produce in other methods. So the CNC application, there's one of the questions about this in a moment, but this is a video of the CNC. So what we've got is the print head mounted in a deployment box, which sits alongside the spindle. And what you can see here is some additive, and then the retraction of the print head, and then we've got subtractive. Back to additive, retraction of the print head, and into subtractive. This hybrid approach allows us to produce parts that we could never produce in another method. So this 5-axis rotary here is creating a 90-degree pipe elbow that is machined on both the inside and outside faces. So unless we had a curved tool, which we would never have, you wouldn't be able to produce this part in a traditional manufacturing sense. So this is a really good example of being able to use the hybrid approach. So some applications here, so you get the idea of times and production sizes and the cost of parts. So we've got a glass mold core on the left, titanium watch bezels in the middle, and a combustion chamber with a cutout section on the right. I'm not going to read the times for you. That's very easy for you guys to find. And all of this information is also available on the Meltio website, which is super easy to access for everybody. If you run one more, so these are parts produced on the robot. So you can see the more complex geometries here. And all of these are produced through strategies developed in Meltio Space, which is the software Jesus was mentioning. Again, all the information available on the website. I think that might be the last slide. So what we'll do is we'll move on to the Q&A and some of the questions, and we will answer them between us, hopefully. So we've got 6 on there at the moment, Jesus. The first one, the first 3 from Jenny. I think I can probably help with the first couple. So how do we position a part that is going to be repaired? So we would be looking at using a CNC application for repairs, just because you would want to get the surface ready for the Meltio process. So when I've done this in the past, we create a datum from the part, and we have a Renishaw touch probe, and we would work with that. And then we would create a CAD file either from a drawing or a 3D scan or the existing CAD file to produce that. If we were doing that in the robot software in Meltio Space, you could load that CAD file in, and you can use a Boolean operation. So you would load in the original CAD file and then a scan of the damaged part, and the Boolean then will give you the toolpath for just the repair section rather than the whole part. So the strategy there can be developed in the software. For adhering the part to the build plate, we would just use a standard CNC clamping system. So the same on the robot, we would just fixture it as you would any other CNC process. For the tensioners on the machines, there is guidance notches on each of the tensioners as well. So it's a 4mm Allen key, and we tighten those. There's markers. It's usually number 4 on the markers for each one. And then the way to test that is to test the extrusion system and measure the output. So each of the Meltio Smart softwares has an extrusion step measure. So you would say, I'm going to extrude 25mm. And then you can measure that extrusion to check that you've got 25mm to ensure that you've not got any slip or any movement on the tensioners.
What about oxidation? What are the basic safety measurements to be taken while using this printing technology in college or university where students are involved? Well, I believe that your question is regarding the oxidation in the part. We are shielding the area where the part is being printed, where the lasers are focusing, so we are avoiding the oxidation in this area. With the majority of the materials we have tested, there are not an important amount of fumes that are generated. And in this scenario, depending on the material testing, in case that you're going to use materials that really can have some oxidation, we recommend the usage of a HEPA filter. So in this case, you can just take this into account. The amount of argon that is used in the printing process for avoiding any kind of contamination of oxygen in the structure of the part is redundant in terms of the size of the rooms that are being used. We tend to have a flow of around 5 to 10 liters per minute, and the safety measurements that are followed are the ones that I just mentioned before. Are there any parts made by this 3D printer used for biomedical implants? We made several tests. So we made tests in titanium already, and at least for Spanish laws, we needed to get an oxidation, now just going together with the actual question you had before, of 0.11% of oxygen content. This is what we got with our system with the titanium grade 23. That is the one that we were in need for some applications. Applications that can be printed in biomedical implants in the Meltio cannot have the really small size that you can, for example, make with powder bed fusion. The thing that we do is for bigger implants and for other implants that have a size of at least 2 centimeters, we can print them and we can focus in these applications, and you can get the actual properties and the actual oxidation that I mentioned before. That is critical for having a titanium grade 23. That is the one that, at least here in Spain, is the one that we are able to use for the implants.
The safety question is a really interesting one. But for oxidization, as Jesus says, we locally shield the part with an argon collar that is shown at the bottom of the print head. But the safety features, so a lot of the colleges that we work with here in the UK, there is a full interlock system built into the machine. So there is no ability to make any moving parts or any laser fire without the interlock system being engaged, which means the door must be closed to give you a certified class 1 laser. And then the only bit that can move is the feed system. So you can only feed material through through the system. There's also a triple filter in there as well. There's a HEPA filter and 2 other filters as well to filter out any particulates in the atmosphere as well. So it's a highly safe system for deployment in education. We've got one more at the bottom from, a couple more. One from Sanjay. Is the melting due to the current conducted through the wire and the base, as with conventional welding, or by direct laser energy? If not directly by laser, what is the function of the lasers? So the lasers are doing the melting. So we've got the 6 lasers which form the melt pool, and the lasers melt the wire to give us the weld. So it's laser welding technically. The idea of using the current through the wire and the base is for process control. So that allows us to ensure we've got the density of the parts and the control of the welding process. As a byproduct of that, we can increase the current that runs through the wire and speed up the process. I'll let you take the next one for, I'll let you take the next 2. Jesus, you can do those.
Yes, yes, I can see. So what is the heat transfer rate? The heat transfer rate depends actually on the power that you are using, and also if you are using hot wire. The joules per second that you are going to deposit in the print really depends on the factor. First of all, the absorption of the material, that with stainless steel, synchronous deterrence is really high. And depending also in the usage of the hot wire. The hot wire capability at the end is able to give you a really high amount of joules together with the laser power that we are using. I cannot give you like an exact number, but those are the variables that are just applying depending on the materials that you are printing. For aerospace, we need aluminum applications. Can we print aluminum? So aluminum is a material that is right now in our developer map, and that we are going to give really good news in the near future. Also, you are invited to an event that we are holding in March that we want to show you something. And maybe we can talk about these kind of applications that a lot of customers are just asking for: aluminum, copper. Just be aware of our newsletter and also about the communications that we do directly by mail and to the people that is adhered to our newsletters and our communications. And you will be really happy about the news that we're going to give you in the short term.
Excellent. Are there any further questions before we start to round off proceedings? In the meantime, just while that's happening, for anybody in the UK, education or otherwise, I am happy to answer any questions. We have numerous sites in the UK, including a showroom in the Northwest, where you're welcome to visit and see the Meltio technology and the applications. And then globally, I think people can reach out to Meltio centrally, and that can be distributed to the relevant partners in your territory. As I say, Meltio is a global ecosystem. We like to refer to it as a global family, where we have a lot of contact with each other, particularly as we look at education, and the spread of research is great for us to be able to unite education authorities from different countries and share and multiply that research to get everything through. So I hope everybody's enjoyed today. It doesn't look like there's been any more questions. So as I say, reach out to your local partners or Meltio centrally for more information. And we hope to see you on the next webinar in a few weeks.
Thank you for coming. And well, it's my pleasure to be able to hold this webinar together with our dear partners from 3D-Byte. See you soon in the next one. I hope you enjoyed.